Good afternoon. I am going to wait another minute or so. I see there's quite a few people busy joining in the last minute or so. So I will wait until 1 or 2 minutes past 12 and then commence the webinar. Good afternoon. Welcome to this webinar on behalf of the University of the Witwatersrand and the South African Institute of Physics. I am Rudolf Erasmus from Wits University and also an SIP Council member, and I will be chairing this webinar. I'd like to arrange that the question and answer session take place after the conclusion of the webinar. So if any questions occur to you during the presentation, please make a note of them, and there will be opportunity afterwards to post the questions either via the Q&A box or the chat box, or by raising your hand if that facility is available to you. So our speaker is Professor Bruce Malado. He is the director of the Wits Institute for Collider Particle Physics and also a senior researcher at the NRF's iThemba labs. He obtained his PhD from Columbia University and is currently the chairperson of the institutional board of the tile calorimeter and the national contact physicist of South Africa at the ATLAS experiment at CERN. He is co-chair of the Nuclear Particle and Radiation Division of the South African Institute of Physics and is the recipient of several awards and fellowships, and he is also a B1 rated researcher of the NRF. Professor Malado is an expert on the Higgs boson, a subatomic particle that is thought to give matter its mass, and was a leading participant in its discovery that was announced in 2012 and led to the Nobel Prize in Physics being awarded in 2013 to Francois Engelert and Peter W. Higgs. Professor Malado is a member of the Gauteng Premier's COVID-19 Advisory Committee, where he leads work on predictions. He is the co-president of the Africa-Canada Artificial Intelligence Data Modeling Consortium in partnership with York University and other institutions in Africa. This project received grant awards from the IEEE, the IDRC, and SIDA. The project also includes partnerships with IBM, and Amazon. I have the pleasure in asking Professor Malado to give his presentation with the title "From the Discovery of the Higgs Boson to Modeling COVID-19, the Role of Artificial Intelligence." Over to you, Bruce.
All right, so can you see me, hear me, and see the slides?
Yes, thank you very much.
All right, thanks, Rudolf, for the introduction and also for the invitation to give this talk here. I've given these talks on other occasions, but I made some modifications. So this will have a connection with what's going on in particle physics and the SKA, which we are very excited about. All right, so I'll say a few words about the science. It's very important to bear in mind that even though we're doing a lot of technology transfer and applications of our knowledge outside the realm of fundamental research does drive the conversation and does drive our agenda. And all these efforts we have developed and will develop in tech transfer really revolve around reinforcing the role of fundamental science. And I will try to make a case about how important fundamental science and fundamental measurements are to push boundaries. And I will talk about the discovery of the Higgs boson at the Large Hadron Collider. After a brief transition and the connection with what's going on or what the SKA can do, I will say a few words, some showcases, if time allows, as to how AI that we learn how to implement and use and understand in particle physics was implemented for the modeling of the pandemic in South Africa. In particular, the work I will present was used to advise the Premier of Gauteng in this crisis. All right, so if we look at matter, and this is what particle physicists do, they look at the fundamental interactions of the smallest constituents of matter in the universe. And as we know, the matter that is tangible to us, that we smell, that we touch, is made of atoms that has electrons floating around nuclei. We now know that the nucleus is composed of protons and neutrons, but we also know, as we increase energies to study matter, that protons and neutrons are not fundamental particles. They're made of something that is even smaller, made of quarks and gluons. So the standard model of particle physics today is composed of a bunch of particles, which are fields, and a bunch of interactions that are materialized through the exchange of bosons. And you see here in a compact way the number of quarks and leptons that we have and have already verified to exist in nature. And they all have a set of quantum numbers. And then there's interactions between them, and forces are enacted. Now, the Higgs boson, since the inception of the standard model, in the 60s, 70s, it was a process. It didn't happen in one day. Of course, the Higgs boson plays a very important role in that it allows to keep the standard model self-consistent and at the same time provide mass to particles, because mass terms in the Lagrangian are actually a very nasty thing. And you really need something, a mechanism, in order to provide mass in a natural way. And it was formulated in the 60s, and it took about 50 years to discover. So that path from inception, from the conceptualization of the mechanism and the field to the discovery was a very long, painful path that scientists had to walk through and ask fundamental questions and push scientific boundaries. This is where we are. The Large Hadron Collider was designed in order to discover physics beyond the standard model, the TeV scale, but also, of course, the discovery of the Higgs boson was a cornerstone and remains a cornerstone of the physics of the Large Hadron Collider. Given that previous accelerators didn't manage, it was designed in order to say, now is the time, we're gonna nail it if it is there, and if the standard model Higgs exists. As you know, South Africa has a robust contribution through the SA-CERN program, and where South Africa participates in the Atlas experiments, Isolde experiments, and has a contribution to theory as well, where you have basically a complex system of magnets and RF cavities that accelerates protons and forces protons to go in a circular trajectory. And you have caverns where the experiments are located that take data, and you can think of these experiments as cameras, very complicated cameras that take pictures very, very fast, creating the big data problem. Now, the experiment that I've been a part of for almost 20 years, the Atlas detector, one of the discoverers of the Higgs boson, is one of the biggest detectors ever put together. It's about 40 meters long and 25 meters high, and it sits around 100 meters underneath the surface in the boundary between Switzerland and France. And you can see here the path that the protons follow that run clockwise and counterclockwise with a very complex system of magnets, the protons are focused to have these clouds of protons collide, go through each other, so that protons collide head-on. And then the debris are basically observed in the Atlas detector. Of course, this is a long story, but we typically, what we do in order to illustrate what we do in particle physics, you can see here in a schematic 3D picture of the Atlas detector, where protons come from the right and from the left. The protons are collimated in such a way that the clouds will meet at the center, and then debris come out of collisions. This is a particularly beautiful and spectacular event where a Higgs boson candidate decayed into 4 muons, and the muons are very clean signatures in that they escape the detector, but they leave a lot of traces that allows the different subcomponents and sensors to establish that a muon went through, and that you can reconstruct what happened. And this is really, in particle physics, one of the most beautiful events that we've seen. Now, the way the Higgs boson was discovered was basically on the basis of a complex statistical apparatus where you keep taking data, you keep collecting data, and you don't know which event is a Higgs boson on an event-by-event basis. Just keep collecting. You just expect that there is an accumulation of data in a certain area that is incompatible with the background-only hypothesis, as you see here. And what we're going to see now is a zoom in into the region of the X's. You see, we didn't know which were the Higgs boson, but we know that the Higgs boson was there. And this is obviously a very strong statistical fluctuation on top of the red, which is the background without the Higgs boson. You can see as the data accumulates, how the events accumulate and how you gain confidence through unbiased statistical methods that something is there in the data consistent with the standard model Higgs. This was one of the channels with these 4 leptons that I showed you earlier. But another important channel is when when a Higgs boson decays into 2 photons. Now, this is a tougher channel because photons are harder to deal with experimentally, and there's a lot more background. But you saw there that gradually, as we were taking more and more data, there was a clearly structured excess of events consistent with the detector resolution. Then you run your statistical apparatus, and then you conclude that something is incompatible with background only, and that is compatible with the standard model Higgs. So that's how it was discovered. This was, of course, a major event in science. I think probably the most mediatic so far. In July 2012, you see here the picture in the New York Times. So the team that led the discovery, you can see me there with a lot less white hair. Obviously, when you go back and remember those times, you remember that very fondly as to how the whole thing evolved and the whole thing exploded, and the discovery was made, and then the interactions with the press and the public. But we have to look forward. That was in 2012. We are now in a different era in particle physics and the physics of fundamental interactions, which is extremely interesting. That's why big data, artificial intelligence plays a more prominent role compared to the Higgs boson. And that's why we, as an institute, and also many in the country, are going towards in the direction of artificial intelligence. Artificial intelligence allows you to learn from the data, and we in particle physics have entered a new phase and a new era, in that we no longer have fundamental predictions to guide us. We no longer know exactly what to look for. We know that the standard model is incomplete. We know that our description of nature and fundamental interactions is inadequate, to say the very least. We have a lot of phenomena that are not described, like additional matter in the universe, the mass of neutrinos, internal inconsistencies of the standard model, and the list of problems are CP violation, and a list of problems basically keep piling up. We know that what we know is incomplete or even wrong. But the question is that now we don't have a theory or an advanced model such as the standard model to say, look there and you will find something. So we have to turn the data analysis upside down. We need to turn the scientific method upside down, in that now we have to learn from the data. We have to devise methodologies that work fine and worked very well for the discovery of the Higgs boson, as you will see in a minute, through machine learning, but now we need to use a different approaches that allows us to learn more from the data, because there is no theory that guides us. Back in 2015, 2016, our team was the first in the world to locate a number of anomalies in the data that now have become, of course, unbearable and statistically compelling. You see here a graph with the incompatibility of the data with the standard model, which back in 2019 was 8 sigma, now is way bigger than that, with a model that we call the Mandela boson model that has made predictions that have come to fruition. And one of the important aspects of what we do is that these excess in leptons that we predicted and now have come to fruition also appear in astrophysics. And we're very excited about that. And a paper is going to come up soon from our team in collaboration with astrophysicists, that the SKA can actually shed light into the nature of these multi-lepton excesses that we also see in astrophysics, not just at the LHC, but also in astrophysics. And we've spent about a year working on it, and now the paper is out and it's already advanced. And what you see there is that we're able, through the model that is able to describe the multi-lepton anomalies at the LHC, the Mandela boson model, through the dark matter annihilation, you create this excess in leptons that are charged. Because they're charged, they are generating synchrotron radiation, and the synchrotron radiation can be detected at the SKA. And you can see here that the model that describes the excesses, that incorporates new physics that describe those excesses, is actually attainable with the MeerKAT, with about 100 hours of running. And that's extremely exciting that we have already in South Africa something that works extremely well, even above expectations and specifications, that we can go and study from the point of view of dark matter annihilation, leading to standard model particles. And that is extremely exciting. All right, so now I'm going to transition to why us. I mean, we do all this science. We're very excited about what we do. Sometimes we are too proud of what we do, but that's fine. That's a driver for a scientist. But why were we picked, and why were we asked by government to help with modeling the pandemic? And I will make a transition from where we were and where we are now in that space. Now, one has to bear in mind that the problem of the Higgs boson discovery was a very complex problem where big data and machine learning were intertwined. Because you're looking for something very small in a haystack, a needle in the haystack, and you have to really appeal to very sophisticated data analytics. And this is a paper that we wrote back almost 20 years ago when I was a postdoc in Wisconsin, where we were the first to basically say, okay, look, this is very complicated. We have to use machine learning. And this was the first paper that was implemented for the discovery of the Higgs boson at the Large Hadron Collider, and where we demonstrated that the Higgs boson comes with complex features that can be enhanced through machine learning. Now, of course, machine learning has evolved. In particular, the implementation of machine learning has evolved tremendously in the past 20 years. We're in a completely different world in terms of implementation of machine learning. I mean, if we look back 20 years ago, we were only really using, learning techniques or supervised learning, which obviously is very good for the Higgs boson, but doesn't really help you with more complex questions that we are facing today. In particular, going back to what I said earlier, that we are now facing a different world. We don't have a theory or a sophisticated model like the standard model to guide us anymore. So we have to change these methodologies and reuse these systems for that purpose. Today, CERN is a powerhouse of training in machine learning, and as a result, SA-CERN has become, in South Africa, a powerhouse in training students and postdocs and academics in machine learning, where we don't really do machine learning development, but we are power users, in that we are able to find applications and ways to most efficiently use machine learning. And there's a tremendous amount of software, websites, tutorials, and it's become really, so to say, a world in its own right, of people exchanging ideas, exchanging software, telling people, making suggestions to people of what machine learning methodologies would work better and all that, where the student and the junior researcher first deals with visualizations and later gradually gets into the complexities of the different methodologies in machine learning and artificial intelligence. So that's now, today, is really a core competency or a core set of skills that our field displays, and is also useful, of course, for the economy in South Africa. So let me move on to now the modeling. So we are there, and back in February 2020, we knew something was going to happen, and then in March, obviously, something had to take place because we're facing the first wave, but we knew very little about it. And we knew also that modeling of a complex system with very little knowledge of what the virus is and does and how it propagates and whatnot is a very difficult task. And it's an excellent ground for artificial intelligence to come in to help scientists and policymakers to learn from the data. And that's what we have been doing for the past year and a half. So initially we formed a consortium with a bunch of SADC universities, and we've been helping not just the South African government, but also Botswana and Namibia, with a lot of connections with Eswatini, Zimbabwe, and Mozambique. So we created a network of scientists, and mostly mathematicians, data scientists, physicists, that speak the same language when it comes to data analysis and artificial intelligence. Later, we got an award from the Canadian IDRC towards the end of 2020, and then the whole thing morphed into a more international consortium that I'm the co-president of, that is generously funded by the Canadian IDRC and other sources, which is called the ACADIC Consortium, with a lot of support now from IBM, as you will see later today. Now, the first step is actually very similar to within physics. You have to monitor, you have to visualize. Before you go and apply artificial intelligence or apply something sophisticated, you have to first create an intuition of the system you're trying to model. You cannot just dive right into it and feed the data into a neural network. That's not how machine learning works. Machine learning requires a step, a previous step, a preliminary step, which goes through visualization. So we developed a dashboard together with, in partnership with the provincial government of Gauteng, and we got an award from the IEEE, where we already started visualizing the progression, the first dynamics of the pandemic, and we created dashboards in Botswana, Eswatini, Mozambique, Namibia, Nigeria, and Zimbabwe. Now we have a bigger pool, of course, and that actually played a very important role to really understand not just the situation in South Africa, but what was going on around us, because we're not isolated. The dashboard has been growing. Now this is an older slide. It has a lot more information. We have added to this mobility, Facebook, Google mobilities. We've added social sentiment analysis with natural language processing from tweet and data, and indexes with artificial intelligence. So it's certainly been growing gradually, and a bunch of other things. I really encourage people to look at the link there to get a state-of-the-art understanding of the structure of dashboard. We created partners in the SADC. One of the best dashboards, in fact, is maintained by our colleagues in Eswatini, that developed a very nice, very easy to use tool that allows citizens in Eswatini and government to really understand what's going on with just a glimpse at a number of visualizations. You want to turn something complicated into something that is easy to fathom and easy to process, especially when you're working with policymakers. And I should make a point here is that we have an additional challenge. You can do artificial intelligence, but you have to convey the result of AI to policymakers. That's the ultimate goal, because you really want to help the ecosystem. We have developed quite a comprehensive dashboard for South Africa. This is an old dashboard, of course, and it is actually today is the most widely used dashboard in South Africa, given the stats we get. And it's used by many professionals, doctors, policymakers, people that really want to get into the analytics of the problem. It's not necessarily a dashboard in the broad sense of the word. And then we provide different kinds of visualizations from different angles that allows the experts to understand where we are in the pandemic. So then we're going a little bit, now that we have an intuition of what's going on, we now have to add some mathematics before we apply artificial intelligence. So we did, we developed a baseline model that was used as a baseline for the province to predict what's going on in the province, to make calculations as to how many beds we need. Is the province ready? How big the waves will be? How fast will it grow? How fast will it go down? So those are questions that policymakers ask because they need to do planning and resource allocation. So we basically concluded that the best way and the simplest possible model that you can use that incorporates sufficient enough information and sophistication is the dual SIRD model. I'm not going to delve into the question of these compartmental models that have been around for a long time, but basically what we try to model through a physical system of two containers. One container would basically have the people that are symptomatic, that interact with the healthcare system, but then you have a much bigger pool, a much bigger container that interacts with it of people that are asymptomatic, because this is a very particular type of virus, is highly contagious. The reproductive factor in laboratory conditions is way above 1, and the majority of the people are asymptomatic. So you have to develop the math that allows you to model that system, and we came up with this model where the important parameters are the stringency index, how stringent the non-pharmaceutical interventions are, and the efficiency of those non-pharmaceutical interventions. Now we become, of course, a lot more sophisticated a year down the road in that we also use social sentiment data, Twitter data to understand the level of adherence. And that's very important to really establish where we are going in the pandemic. And then you run your math in your equations. These are not very complicated questions. These are first order differential equations, and then you bump into some numerics, but you sort of get a feeling of the applicability of the model and where it can and cannot be applied, and you're able to provide predictions. All right, so the first thing that we needed to do once we had this mathematical apparatus is to develop a stringency index for South Africa. That's the first thing we did. That was the first thing that was done in order to be able to help policymakers in the context of the alert system of South Africa. Remember, we have a 5-level alert system with a bunch of definitions and a bunch of actions that are taken in order to curtail social interaction. And social interaction is the core of the transmission, of the community transmission. So what we had to do is we modified a methodology developed at Oxford for the conditions of South Africa and within the context of a 5-level alert system. And we provided a level of stringency as a function of time, and that helped us make predictions, because policymakers want practical solutions, practical predictions. They want us to answer the question, what happens if we now open the schools or and we keep other restrictions, or vice versa? Those questions need to be answered, I wouldn't say in real time, but within 24 hours. So you need to have this mathematical apparatus under control, coupled with the stringency index for South Africa. Because you need to answer a very practical question that our committee answers on a regular basis when we interact with the Premier and the Premier interacts with Cabinet. When do we go from one level to another? When do we release restrictions? When do we tighten the restrictions? You cannot make a thumbsuck. You cannot make, oh, let's do this, let's do that, and see what happens. That's unacceptable, because there's a lot of people are going to die. You're going to spend unnecessary resources or underspend, which will lead to unnecessary loss of life. So you have to be rigorous, or at least within the context of the linearization of your model. You have to linearize your model and come up with inequalities that allow you to establish whether we are ready or not. And this is a slide we showed to the minister and Kise at the time, illustrating that at that time we could move from level 4 to level 3. That was at the end of I remember the first wave, if I remember correctly. And they would say, okay, this number is bigger than that. We are ready to move because we have gained certain ground that can be lost by releasing restrictions without losing control over the pandemic. It's like walking on a razor's edge, but it has you have to provide a procedure. You cannot come up with, oh, I'm a professor and I advise you that. That is not the way. And in fact, policymakers are very smart. They realize, they understand very well what is the methodology you're following and why you think you are right, or at least that your advice is a sound one. So it doesn't work like, oh, I'm going to tell you that and you're going to take it. No, they interrogate things very, very deeply. And it took us about 6 months or so to gain that relationship of trust, where they really said, okay, I think I understand what you're trying to do and what you're trying to tell me. And I believe you're right. And then obviously practice, thankfully, proved that the modeling more or less, especially when you extrapolate within the next few weeks, works, generally speaking. So once you go deeper into the time evolution and the time series, you basically start running your models and all that. And this was basically right before the first wave. We can see here, let's focus on the red points. This is the number of cases. It's not important, the discrepancies on the other two curves is not relevant. We don't have time to explain. And what happened here is that around the beginning of May, the data was seriously overshooting the model. The model was not incorrect. The model had assumptions and has an output. What happened here is that we basically encountered a new dynamic in the pandemic, which is very different from the stochastic approach that people take typically in epidemiology, that required implementation of artificial intelligence, and that is the development of hotspots. And you can see later when we went into the first wave, this probably was the second, I don't remember, first or second wave, doesn't matter. We basically saw that I think this was second wave. No, excuse me, I take it back. This was first wave, excuse me. That was the middle of last year. And the second wave was the beginning of 2021. And what you saw there, that as the pandemic was progressing, the stochastic modeling was not describing the data. And this is not because it was wrong. It was actually doing the right thing. It's just that you had a new dynamic emerging in the province. And that basically brought us to the first big artificial intelligence-based or powered project, which is modeling hotspots with artificial intelligence using clusterization techniques that come from unsupervised learning. And this is a paper to appear in a leading journal internationally. And what you basically do, because you know that it's very difficult to predict clusters of cases because it's extremely dependent on the local conditions of the community. And there's a lot of factors that enter. What you do is you basically say, since I don't have that knowledge, I'm going to turn the problem upside down and I'm going to clusterize and try to learn from that clusterization. And what I'm going to do is that those clusters are going to become mini pandemics. And I'm going to try and test whether epidemiological models work. And actually, surprisingly enough, they did, on the basis of the input from artificial intelligence. So this is what the animation here is basically trying to tell you roughly what we tried to do. Then we partnered with IBM, and IBM provided a fairly sophisticated visualization technique. They did a lot of software development where people could go in, out, go down to even the level of the street to really understand what the cases were. And this actually helped a lot policymakers dealing with the problem of what to do, when to do it, and where to do it, to understand where the hotspots were and how severe those hotspots are. We created a risk index based on this outputs from AI. We developed a risk index to help policymakers understand where the severe, the dangerous hotspots were. These are hotspots that grow very fast, that absorb neighboring hotspots, that have a quasi-exponential behavior. And when we calibrated that with statistical techniques, we basically provided a threshold above which we deemed the hotspot dangerous, and that helped policymakers focus on the most dangerous one, because at peak you have around 200 hotspots or so. You cannot do everything. So that's a very important practical indication. Also, when we monitor social media, we realized that communities were looking at this too, and they were telling each other, my God, our area is a hotspot. And that helped with curbing the pandemic locally. How much time do I have, Rudolf?
About another 10, 15 minutes, Bruce.
Okay, sounds good. I think I'm on time. And you can see here, this is from the second wave, where, and also it's actually a fascinating topic to see how the pandemic moves from one place to the other. And the color code tells you the severity and how certain neighborhoods became first infected, how those infections moved to other neighborhoods. And it was really a fascinating thing. But of course, for, you know, that's for the scientists. Policymakers want action, and this is the action that they need. All right, another important AI-based project was the development of the risk index, which actually was requested by the South African National Defence Force. During the first half of the pandemic, the SANDF was engaged. And they asked the question, when is a pandemic or a wave going to take place? And the reality is, you don't know. And anybody that tells you, oh, that we're going to have a wave in November, October, that is not the result of a thorough calculation, because there's no calculation that can give you the time and the date of when a wave is going to start. Because waves are triggered by non-stochastic processes, super spread events, which are spurious and cannot be predicted. As simple as that. So in order to go around that problem, we basically developed the concept of risk index of waves, where we could have few weeks of time to tell policymakers something is happening, the dynamics are changing, and this is compatible with previous waves. And then we first did a classical analysis that was complemented with an AI-powered algorithm, which was published recently in the journal here you've got it. So I don't have time, so I'm gonna go into the math, but basically what we did is, okay, we have a lot of experience throughout the world. We have a lot of data. Let us do a frequentist analysis of the algorithm and see when it works and when it doesn't. And then we came up with an algorithm that said, well, above this threshold, you have 80% probability of a wave to happen. And we developed that for South Africa. Of course, the parameters are South African. You cannot get parameters from France or Italy or India. It has to be produced through the analysis of local data. So we produce this interactive map, and then you can click and see where you are, and then you can go into the different districts and sub-districts to understand what's going on. And this is now obviously looked at on a daily basis by policymakers for the third wave, for instance. These are graphs for the second wave. Now, what we did is, let's say, this concept seems to work, so now we have to take it up a notch and create a neural network within the context of recurrent neural networks that are used a lot in finance to make predictions. But instead of making predictions in finance, we're going to make predictions as to what's going to happen with the wave and whether the wave is consistent with a situation of equilibrium or a new wave. And then we created an ecosystem of data that was fed into the recurrent neural networks with a simple output that allow us to give us some time to decide whether something is going to happen or not, and also helps us understand whether we are past the peak or not. So this is heavily used in our reports to the Command Council. And you have the paper that where this thing was published, and you have a website there where you can see the risk index, whether it is below or above, and the threshold is decided upon through a frequentist study with a 5% confidence interval of error. And we do that for each province and so on and so forth. And this really helps us a lot understand where we are, because when you look at the number of cases, that's fine, but it can fluctuate. You have to look at the data holistically and put everything together through a comprehensive neural network to really understand whether all the data is consistent or not just one index. So that's a very powerful tool. And the last topic in the last 5 minutes, where AI played a very important role, was the vaccination rollout. And obviously, a lot of the discussions were done closed doors, but it was the first half of the year, especially the first 3 months, were very, very intense in trying to understand how the rollout was going to happen and what is the optimal way of the vaccine rollout given the scarcity, which is a very important boundary condition to the problem. And AI again played a very important role. Now, as a reminder, you probably know that the rollout of the pandemic is phased in South Africa. Phase 1 is already completed, where the frontline workers were vaccinated, and they have been in its immense majority. Then that led to phase 2. We're now currently in phase 2. And the question emerged, remember, you can see here, the first guess was, do people above 60 and then the rest? And we told them, no, that's not an optimal way of doing it. And you can actually save lives if you do it optimally. And that's where AI came in. And then at some point, we will get to the phase 3, but we're now currently in basically dealing with vulnerable populations. And we developed an integrated approach that is fed into AI. This is in collaboration with our colleagues in York University in Canada. But of course, when push comes to shove, and you sit there, for hours on end with policymakers, you realize the situation is much more complicated than it seems. And the answer to a complicated situation is a simple scheme. And that is what we have today. So after a lot of conversations, a lot of weekends, we decided that the best way to go, instead of developing an overarching neural network with all possible factors, we decided to go for a two-pronged approach where artificial intelligence would be fed in at a different level. The first would be to create a system of vulnerabilities that would incorporate all the social vulnerabilities that are relevant to transmission and severe outcome. And that is basically driven by social vulnerabilities. That's one prong. Another one is to deal with individual vulnerabilities and the probability of an individual, given clinical data that I will show in a minute, of the probability of an individual to contract the virus and be hospitalized and or die. And that's where AI came to tell us when is that happening with the highest probability. So what we did was we got data, confidential data. We signed an NDA with government. We got data from hospitalizations, and then we applied methodologies of weak supervision coupled with deep learning to really understand the different types of likelihoods, different types of probabilities of someone to contract the virus and die or end up in ICU compared to general ward. And that helped us classify the different groups into the probability of someone to contract severe illness. And then we developed an algorithm that basically was telling us that, in order to decrease the probability of severe disease by a factor of 5, you need to you have to de-escalate slowly and gradually the groups that you are going to be administering the vaccination to. You cannot just go people above 60 and the rest. That's very inefficient. What you have to do is to do it in a gradual way, establishing a much refined classification, which is what happened in the end. And as you know, the rollout was actually refined at a second stage, that with about 20% of the vaccinated population, you can reduce the probability of severe disease, hospitalization in ICUs, and death by about a factor of 5. As we have seen in other countries. And then we created a classification. We created a classification for the province. And we also, and this was published, I forgot to put the link, but this was also published in an international journal. And then we created, together with our colleagues in the GCRO and the Department of Health, an index of social vulnerability. We created quadrants that would incorporate vulnerability index that are socioeconomic mostly, and population densities to really ascertain where the most vulnerable populations are that need to be taken into account when the rollout takes place, which is basically now. And this was now visualized with the help of our colleagues on IBM. Not only do we have, you can see here, the hotspots and the predictions that we provide, but also the risk factors and this overarching risk index that we generated together with our colleagues from the GCRO to help policymakers understand where the vulnerabilities are located in the province, to help to ensure that wide or large communities or large swaths of territory are left behind because we don't look at these things. So these things can be visualized, and it's a public tool that people can tap into. And I think that is 45 minutes. Thanks, Rudolf, for your patience. And I think I'm done with my presentation.
Thank you very much, Bruce. Much appreciated for that insight into what goes on behind the scenes. For all participants, I have reposted the survey link that we ask you to please complete. It's in the chat. I've reposted the survey so that you can easily access it. It will take 2-3 minutes, and it's Sasta and other people need the statistics there to evaluate the impact of the Science Week. Right, so we can proceed to questions. There's already a question in the question and answer box. And the question reads, can limitations related to data collection on the ground skew the predictions of the models in any way?
That's a very good question. The answer is yes, very much so. And that's where most of the work and discussions go into. I mean, what I've shown is just the tip of the iceberg. But then comes the discussion within the context of the advisory committee with different experts from different walks of life, whether it is clinicians or practitioners, epidemiologists, mathematicians, to really understand these biases. And I can give you an example of a very important bias that we try to alleviate is the fact that in South Africa, the officially recorded death and therefore severity of virus is only a third of the total recorded deaths, which are computed by the MRC using excess mortality methodologies. That basically means that only a third of those that contract severe disease interact with the healthcare system. And that's probably one of the biggest problems that we have. And you have to really start probing the system to really ascertain where the model will fail as a result of that. And it's a lot of work that happens a lot at the level of conceptualization and gathering intelligence from the different stakeholders. We had a lot of help from the WHO and local representatives. We had a lot of help from the Department of Health officials. We basically try to avoid or minimize biases, but biases, unfortunately, especially in South Africa, are unavoidable. Our job is to minimize them.
Thank you very much. There's a related question, I think. It has been estimated that the actual numbers who have COVID are 5 to 10 times higher than that reported. What is your view on this?
Well, that's a well-known fact, nationally and internationally. In fact, towards the end of the year in 2020 and the beginning of 2021, we had a number of seroprevalence surveys that were performed to ascertain what is the fraction of people that were really infected. There was a measurement through random checks in blood tests. That was one way of looking at it. And then the Department of Health, in collaboration with Shabir Mari, who is now our Dean of Health, they did a seroprevalence study that ended about the 15th of January. And both, they more or less showed a picture that round about 1 in 10 people show, okay, let me put it this way, only 0.5 to 1 person tests positive, which is a convolution of many out of 10. So basically about 5 to 10% of the population that got infected tested positive, meaning went to a testing station and got and tested positive, which is a different question from whether that person was symptomatic, because as we know, many people were symptomatic but didn't get tested. So in order to understand an imperfect, with an imperfect data set, the dynamics of the system, you have to understand what it is you're probing. And those seroprevalence studies basically told us that roughly about 0.5 people out of 10, 0.5 to 1 test positive. So most of them, they are either asymptomatic or don't get tested.
Thank you. That's very interesting. Are there any other questions? You can also post something in the chat. I was just wondering, this seems to compare very well with the similar efforts and modeling that's been done in other countries around the world. Is that a correct impression?
I had to say we've been so busy that we haven't followed that too closely. What we've seen typically is that modeling efforts have been kept closed doors. That's my impression, because we haven't really interacted with foreign teams other than some of the SADC interactions. I've interacted, for instance, with with the government of Botswana around some questions. But also, look, the work of our committee is also closed doors. So all the proceedings and minutes and recordings, everything is done confidentially. So to be honest, we never really had serious interactions with teams outside the country. We've had a lot of interactions with teams in the country, but not really outside.
No, thank you. There's another question that's come in just now in the Q&A box. Can you explain a little more about how you incorporate the social media data into the modeling?
That's a very good question. And you can go to our website, you can see the evolution. We can really see, based on social sentiment analysis of the tweet data, that that population cares much less about COVID-19 and social distancing than ever before. Now, the third wave was very different in that regard. And we saw clearly by doing very simple frequency counting of tweets pertaining to COVID-19 tweets that people, there was a lot of apathy during the third wave, especially at the beginning. And then that was very important intelligence that we passed to government in order to ascertain how far you can go in restrictions. Because you see, one of the arguments that was used not to even discuss or consider level 5 was the fact that we knew that the level of adherence would be terrible and it would backfire. So that the social sentiment data played a very important role in arriving at that conclusion. And our advice was very clear when things got very tough. We had a very rough moment when the second half of June, when we were told by the genomics team that the Delta variant had become dominant. It was a very tough time for us all. It was really a very, very, very difficult 2 weeks we had. But at the same time, we said, look, if you put forward something that is level 5 or very strict level 4, you're gonna have a problem. And as a result, yeah, it was very clear that we couldn't do it. And social media played a very important role for that kind of stuff. And there's another question here: is there going to be a fourth wave? Yes, absolutely. The problem we are facing is that we now have a different virus. The Delta variant is much more contagious. The reproductive factor is significantly higher than the original virus, or even the Beta variant that became dominant in South Africa end of the year, 2020. And as a result of that, achieving herd immunity is very difficult, because that means, remember when government said we have to vaccinate 60-something% of the population, that was calculated with a reproductive factor of the Beta variant. Now, Delta is far more contagious. That's known, that's already very well established. So the corresponding number would have to go much higher, very close to 100%. And we know that's going to be a challenge. So yes, there's going to be a fourth wave. And the approach now, when it comes to vaccination, is to ensure coverage. Herd immunity, yes, it would be great if we could achieve it. Nobody questions that. But coverage of vulnerable populations is absolutely paramount in order to turn waves into something that is, that can affect people more mildly, that doesn't lead to massive mortality compared to the one that we had in the third and second waves and first waves.
Thank you very much. I see there's another question that popped up in the chat that we can perhaps first look at. There was a question that said, what period does the predictions account for? Does it valid for a month or 2 months, if you want to predict?
Well, we do two types of predictions for government. One is scenarios. What we do typically, we provide, we think, a certain confidence intervals, a best case and a worst case scenario. That's typically how they like us to present results. So that is something that is used for studies such as gap analysis. Do we have enough beds at peak? And what we do is we always give them a worst case scenario to say this is the worst thing that can happen. And in that sense, I mean, there's really no, in that sense, time doesn't play a fundamental role, because we have the risk indexes to tell us when the wave is going to take place. Now, when you are in the middle of a wave, then you have to be much more careful, because you need to have a very good understanding of what's going to happen in 2 to 4 weeks. And typically predictions seem to be working fairly well. For instance, for the third wave, since it was so big, we really need to have a much more accurate calculation of the number of beds. And we actually got it right within 68%, but that only gives you, so to say, a margin of time within which the prediction is going to be reliable, which is typically 2 to 4 weeks.
Thank you. There was also an earlier question in the chat that said, did you see any similarities in terms of virus infection across the SADC countries?
We don't have enough information about that. This is one of the things that would be great to improve, to have sort of like a better coordination at that level from the SADC region. So our committee, our advisory committee to the Premier, has not received information along those lines.
Thank you. Coming back to the question and answer box, I see there is a question that said, how would you respond to those who are hesitant to get the vaccine?
Well, this is something that government is always engaging with communities, local leaders, spiritual leaders, and it's a very intense part of the job. I mean, right now is not only about vaccinating people and creating the logistics to make that happen at a reasonable rate, which is a very complex logistical problem, but you also have to deal with the problem of how to convey to people that don't believe in vaccination. I mean, many people believe that there are other ways to deal with a disease, and that basically goes through a lot of engagements. I'm not involved directly in that, but it's obviously an effort that's being made by many stakeholders in trying to convey to the communities that the vaccine works. And we know it from international experience that there's a very strong correlation between the rate of vaccination and the mortality rate. Is anti-correlated. And when the third wave is finished, we will have a complete analysis of that anti-correlation in the South African context to demonstrate that vaccines really work. So we do what we can.
Okay. Thank you very much. I think there are two questions related to new variants or different variants. So I think that if I were to paraphrase them, is then has the experience with the Delta variant given you the capacity to quickly adapt your models to the parameters that a new variant may exhibit in terms of infection rate or severity of symptoms or number of people that die?
Yes, that's incorporated in the analysis and the models through a number of parameters. When the minister or the acting minister came up with her, okay, let me give you some history. So on the Thursday, we had a press conference where we conveyed to the population that there was something wrong with the data, that the data was deviating from the modeling, and there's something very wrong with the data. Something was happening. That was the Thursday, and then the Saturday, the minister came up with a press conference where they already informed everyone that the new variant had taken over, that was already present in May, and then around the second half or the middle of June, in KZN, the Delta variant had taken over, and the expectation was that the same thing had happened already in Gauteng, given what we saw in the data. So we obviously had a plan. So we to deal with this sort of situations. Once we were told on Saturday, it was around noon, we basically activated the plan and we redid everything. So by Monday morning, when we had a meeting with the minister and the MAC, we already have the first numerical results. So in principle, yes, it's flexible enough to adapt to changing conditions, such as the one that took place in mid-June in Gauteng.
Okay, thank you very much. And obviously, many late hours behind the scenes involved in getting that done, it seems.
Indeed.
Okay, I think there's been a number of comments in the chat about the great talk and a wonderful presentation. So it's 1 o'clock, and I think I will then conclude here and thank Prof. Malado again very much for his very interesting, very insightful presentation, and also for the whole team behind him and working with him. I think that that play such an important role in making sure that South Africa is able to cope with this virus. Thank you also very much to the DSI and SASTA and for making National Science Week possible and for focusing on this very important aspect in South Africa. Thank you very much also to all the attendees and all the people who posted questions. Thank you very much for your presence and your participation. And as a last comment, please, in the chat, if you haven't yet done it, please complete the survey that the SASTA needs to evaluate the impact of the National Science Week. So thank you very much. Again, I wish you a good afternoon. Goodbye.